Thank you. Hello. I'd like to begin by telling you about something that happened to me in 2005. I was relatively fresh out of art college and had spent my time making things with materials, but on a very human scale. And one day I met a material scientist who put something in my hand, which is this. Now, this is going to be the perfect thing to do at the start when I'm nice and shaky. We need a nice close-up on this and of me wobbling. Perfect. Okay, so I have in my hand a material called Aerogel. Now, at the time, in 2005, this was the lightest solid on Earth, like the lightest stuff there was that was solid. And it was developed by NASA for catching space dust. Okay, they would take it up into space, drag it behind the tail of a comet, and lots of interstellar bits of dust would lodge themselves in this material, and they'd bring it down to Earth and examine it. But this blue color, this is not because of a pigmentation. This is not blue for the same reasons like my t-shirt's blue. This is blue for the same reasons that the sky is blue. This is the way in which light is scattered as it passes through at something called an index, which is Rayleigh Scattering, and we perceive that scattering as blueness. And the scattering is caused by pores of the material, but the pores are tiny, like down at the nanoscale, and we'll come on to that. But they're pores that make this material a foam, but the foam is just so fine you can't see those pores. And it's just a poem of a material, really. And I'd spent my time making things out of stuff, and then suddenly I was confronted with the most extraordinary material that I could possibly have imagined. As I said, a poem of a material. And I realized I couldn't make anything better than this. You know, I couldn't make anything out of it. I just had to sort of communicate its story and show it to people. So thus begun this journey of a collaboration, really, between arts and sciences, design, engineering, musicians, bakers, doctors, nurses, all around materials and the things we make with them, and the building of a collection of materials. But along the way, I kind of learned a lot about material science and did a PhD and sort of became a sort of undercover material scientist in some respects. But for me, this is all about the combination of the arts and craft, design, engineering of stuff that is all around us. But if you asked a material scientist, yes, there is going to be a test. So, yeah, no. If you ask a material scientist what is a material, it's actually a kind of difficult question. They talk about categories and they talk about structure and properties, and perhaps they would refer you to this, the periodic table. But really what we have here is a map of concepts, a map of ideas, the fundamental building blocks of the world around us that you combine together to make our known world. You, me, the air we breathe, the wood of this stage, the material of this table, are all made of something, and it's all about combinations of this stuff. But actually, this is about the atomic properties of the material and the idea of them as a pure element. But actually, when you get things in the world, if you took element number 29, for example, copper, Cu on the periodic table, that tells you something about its properties in relation to the others. It's in a specific group. It maybe has a specific valency, so ability to conduct electricity. You could extrapolate from knowing its position and a number of protons, neutrons, and electrons of that atom, put it in that place in that table. But actually, when you get a bit in the world, actually, maybe you have a copper spoon, or maybe you have a copper tuning fork, and they're different objects, they're different things, and although they have this heritage of copperness, actually you could scientifically test and prove that they have different properties, they are made of relatively different things. This one's oxidized, this one not so much. They're kind of different materials. So where does material start? Are materials atoms? Does it go all the way up to spoons or computers? Is this the whole thing a material? Or is it made out of materials? But this is a sort of bone of contention, really, like where is that point where material starts? So this is the fundamental map, but the other thing that's very important to science is this notion of scale, really, and the length scale, because the material scientists spend a lot of time down inside materials, fiddling about with them to give them different properties. But the best way to kind of talk about this is to start with the column on the left, the animate world, because this is something that kind of culturally we're pretty used to. The idea that actually if you look at me and zoom in, you know, and you suddenly start to see things that you couldn't see before. So and you look at the mouse, be the same. Maybe you zoom in on the mouse, an order of magnitude, and you'd find a little flea on the mouse. And you could zoom in again on the flea, and you'd find a little hair on the back of the flea. Then you could go inside the mouse, and you'd find tissues. And then looking at the blood, there's some red blood cells. And then structures inside the cell, all the way down to something like DNA, so fundamental molecules, excuse me, the building blocks of life, essentially. And we're used to this idea that DNA is a code. It's a code that tells you specific instructions of your body, how to develop and what to do in terms of the structures to grow. So in every cell of my body, there is code that says when you grow hair, like grow dark, kind of quite thick, curly hair that's a little bit unruly. And you see that macro effect of a code that's absolutely down at the nanoscale, this code. And so there's a relationship between the two. But if I was to zoom in for a moment, so here I have a microscope that's slightly out of focus. Let me just do that, okay. So I have a microscope, and you look at my hair now, zooming in. But then we go something like here. Now, look, hair. Yes. If you saw me, you wouldn't think this woman has a moustache. I hope not. But look, okay, we've gone in an order of magnitude, and you now see something that you wouldn't have seen before. All right. You can have a lot of fun with this later. So you've zoomed in these order of magnitudes, and you see things that you didn't see before, and you see structures, and this can go. But they can talk to each other. I could mechanically straighten my hair with heat, or I could chemically straighten it with the chemicals and make it straight, so change its structure by attacking it at different scales, or applying a molecule to it, for example. And so those scales change. Or I could be exposed to radiation and have some damage to my DNA, and then my DNA mutates and would then grow a tumor, and then I would see a lump. So you have a macro effect affected by these sort of micro internal structures. So that's the kind of living world of matter, but actually materials in the inanimate side of things are very similar. There are scales in which there are structures, and those structures have relationships between them. So if you were to zoom in, so inside this computer, you'd see tiny wires, and you can make now little cogs and machines that are very, very small, about the size of the hair on the back of a flea, so much smaller than the hair on my head, little working machines, little cogs. And you could zoom into metals and start to see the structures that they're made out of. So here we have some, on the micro scale, we have some metallic crystals. You can zoom in and start to go to arrangements of molecules all the way down to single atoms. But these scales talk to each other. And to kind of illustrate that, I just want to briefly pause and tell you a little bit about metals in particular. Because again, culturally, we're used to these ideas of them homogeneously, like probably grey and like impenetrable industrial stuff is metal. But actually, the minute you start to zoom in, you see something different. So here we've got the scale of my hair, and if I just paste this on the computer, you suddenly see it's kind of granular, right? Now, what you're looking at there are metallic grains, single crystals, because all metals are made of crystals. So again, counterintuitively, we use the word in culture to kind of describe crystals as something maybe like hippie rock and gem shop style things, like these crystals, or maybe glass is crystal, but it's not, or it's the things that grow, but maybe ice crystals people start to think about, but you don't think of metals when you think about crystals. But all metals are made of crystals. And the process of metals becoming solid is one of crystallization, of the growth of crystals. And so what happens is you've got to imagine you've got your liquid metal, and little points in the liquid start to what's called nucleate, which is to grow a crystal from them. So here, a crystal is seeded, and a crystal starts to grow. Here, maybe one grows. Here, one grows. Here, one grows. And they start to grow, and then when they touch each other, they sort of stop, and they form a boundary. So that is a metallic grain, and this is the grain boundary. So in very simple terms, this is the structure down inside the metal. But if you were to bend the metal, for example, here's some, if I can bend that, what's happening there is those grains, they can move and they'll slide over each other. So something like ductility, which is just bendiness, right? That depends upon crystals which are able to move over each other. But if an engineer was to design crystals that locked into each other different, or put impurities in between the gaps so they had nowhere to move, you'd end up something very, very stiff. So that would be like adding carbon into iron to make steel. And then you end up with something very strong, and it's not got any ductility to it, no bendiness. So anyway, these crystals inside metals. but they're tiny. I mean, you don't go around looking at, oh, look at that grainy metal. This looks homogeneous, smooth. You know, they're known for that smoothness that you can get to metal. But, as I said, when you start to zoom in, you start to see grains. Now here I have a sample which has some very big crystals on, so hopefully the camera can pick this up and start to see that with the naked eye now, you're starting to see the grain pattern of this material. This aluminium is being cooled really slowly. So if you let the material turn to solid slowly, so you cool it slowly, the crystals get a chance to go really big, and then you start to see them. So this is big scale. Now, I don't think I can pass this around in the space of the time I've got left, but anyway, hopefully the camera's picked that up for you to see it. But you could see this with your naked eye. But what I want to show you now is one ginormous metallic crystal. This is a single crystal jet turbine engine blade, and it's one of the most extraordinary things we as humans have kind of ever made in some respects. It's sort of the pinnacle of our relationship to metals. We have defined our civilizations by our relationship to metals. We think of the Bronze Age, the Iron Age, copper, and the Stone Age. You know, materials play a massive part in defining what the technologies we've been able to make with them. And this really says a lot about the last 100 years. Because without this, you wouldn't have jet engines. So just to quickly sum up how it's used as an object, this gets cut off, this bit gets inserted into a blade, and the one blade gets inserted, you make the turbine, and you have your engine. So when you see the engine off the plane, it has very large blades at the front. They're there to gather the oxygen, compress it, move it to the back of the engine. Fuel is injected, it's ignited, and you have a huge explosion, controlled explosion that happens around these things, and they spin, and off you go forwards. But that's massive temperature, massive pressure. The centrifugal force on this is extraordinary. So any other metal, those grain boundaries between the crystals, that's a potential crack, and boom, it's exploded. So they needed to make something with no cracks. And how they did that was to grow it as one crystal and get the crystals to grow in this direction. And you cool it very slowly and you pressurize it, and the crystals grow, and they hit this helix. And crystals, they kind of grow a bit like Christmas trees. They've got these dendrite arms. They're moving up through this helix. And eventually, one crystal sort of penetrates this whole area and then is allowed to solidify the whole shape. So you cut it off, and that goes in. But, I mean, you can fly, right, because of aerodynamics and lift, but you can fly fast because of jet engines. And you can only have jet engines because of this material. And when it was invented, it wasn't named after someone, it's not Zoe's metal. But it was just called a super alloy. It was just deemed so extraordinary that this is just a super alloy. And it sort of tells you the lengths to which we go to engineer materials, but also the cultural impact of them. I have here one other metal which I'd like to show you. The camera should currently be above me, so you can see down onto this plate. Is it? Just tell me when Okay, ready. So here we have a material which is made of nickel and titanium. So it's a nitinol alloy, and it's a shape memory alloy. So some of you may have seen this, but for those who haven't, I will show you what it does. Yes, for the paperclip. So what was happening there? That was crystals performing for you. On this ginormous stage, the crystals did a performance, basically. I bend it, they move, but it's inefficient, they don't like it. If you give them the energy, if you give them the means to, i.e. the energy or heat, those crystals will transform. They will realign themselves in the position they were when they were first made. Okay, so in this case, they orientate them back into the shape that we programmed it to be, which was paperclip. But what I love is that this tells you so much, again, about the material world, out of what we make, out of our ingenuity. Because instantly, that was moving, and you suddenly thought, oh yeah, now I know what that is. It's a paperclip. You recognize the shape of it. But you think, oh, it's just a boring old paperclip. But actually, paperclips are extraordinary things. This won't function as a paperclip. It's not stiff enough, right? I couldn't put paper in that and keep it together. But just that simple expression of a shape made out of steel in the shape of what we call paperclip, and it does an extraordinary thing to perform and be that object of holding the paper together, but being also bendy enough that you could unpick it and pick a lock. Like it's that perfect balance between stiff enough but not too stiff, And yeah, just in one simple object, there's so much material science and engineering and kind of wonder to be had. And I now see that I've only got a few minutes left. It's precisely 3. So I'm going to show you some of my favourite materials, but in a slightly whistle-stop tour, ending when I've got 2 minutes left with some liquid nitrogen demonstration. Okay, so I have to put on this because I don't want to freeze myself. Right, so the collection that we built up has all sorts of things in it, ranging from tin, can you hear that? So this is a metal that's ductile, it's bendy, but it's also kind of crispy and crunchy. But this is the crystals again. This is the crystal structure inside that material, grinding over each other, kind of like popping past each other, producing vibrations, producing sound, and producing a kind of tingly feeling. Here we have a material. This is 100% steel, but it's been knitted. I can show you on the microscope the kind of scale we're looking at, how fine this really is. If I pull out some hair. Okay. Here's some hair. And now I'll show the end of one of these yarns. Oh my God. So maybe I can get both in shot. This would be a triumph. There, so you can see each individual strand of that steel is thinner than my human hair onto something else. Fast and furious. We have a ceramic. This is the second hardest stuff after diamond, right? So only diamond will scratch this, but it's a ceramic. So it's kind of counterintuitive, right? So if I was to throw this ceramic on the floor, we kind of know what would happen, but no, maybe not. So tempting. But maybe, yes. Okay, so, but this, I can just drop this. Now, again, you won't be able to see it, but that's left a dent in the wood, okay? I didn't throw it, but it's left a dent. And that's because if I dropped another ball, right, the ball would give and bounce. But here, this will not give at all. Only the floor has to do all the giving, and it hasn't got any elasticity, so it doesn't recover, and you're left with this crater. But I wonder, yes. I think over the top camera. So the ceramic plate had to do all of the giving on that respect. Okay, right, drink of water. But talking of ceramics, I have here a very sad and slightly damaged ceramic because it's very fragile, as we've seen, most ceramics. And I've attempted to super glue it back together. Now, I know it's not a good idea to try something the first time in front of 2,000 people, but that's exactly what I'm going to do. I'm going to attempt to show you one of the extraordinary properties of this ceramic. So this is a superconductor. This means that when electricity passes through it, it barely resists it. Normally, when electricity passes through a material like copper, the material warms up, you lose some of the electricity at the end. It's inefficient. But through this ceramic, it conducts it without any resistance. But that only happens when it's minus 190 degrees Celsius. Okay, so I'm now going to cool this down to minus 190 degrees Celsius and hope that my superglued DIY hack of the, of the ceramic holds it together and that this works. So we have to let this cool down. So this is boiling, essentially. This is very, very cold, and pouring some on this surface is the equivalent of pouring like water onto a very hot oven or something, right? It boils and is evaporating and giving a nice cool, toesy feeling to the front row. Right, the thing's flashing. Time's up. Here we go. Now we have a magnet. Magnets pass through materials generally without interfering them with any respect. Cork, nothing doing. Tin, nothing doing. Steel, magnetic, pulls it to it. The magnet, ceramics aren't magnetic. No, nothing doing. Here's another piece of this material here. The magnet's having absolutely no effect. But now it's very, very cold. We should see. Thank you very much.